Hey and welcome. Today we are going to solve same tree interview question. We will walk through both BFS and DFS solutions for this, so let's get into it. First example here. We have two subtrees and every single node of them has the same value and placed in the same subtree location. We have one as root, two in the left and three in the right. So we return true for it. Second example, we have one as a root, we have two as left node in here, but we have same two as right node in here. This is the hint of this example. Even though nodes have the same value, but they are not in the correct location in both subtrees. So we return false for it. And last example, we have exactly the mirror version of the left subtree in the right. So since they are not following the rule of every node in the exact same location, we are returning false for it. Let's see how we are going to solve it. In order to solve this problem, as a normal tree problem, there are two ways to approach this, either using BFS or DFS. I have short videos for both if you are not familiar with them, or you may need to refresh your mind on those topics, so please check them out. But I'll explain both solutions here so that you can get a clear understanding of how to solve this problem in either way. First of all, the intuition for solving this problem is kind of easy. The baseline is that we need to iterate both subtrees at the same time and check for every node. That is the only way that I can think of, at least. Of course, I would not be surprised if you comment out some innovative ideas to solve this, but within this check process, there are some cases that we need to keep an eye on. So if both nodes from both subtrees have the same value, we are fine. We can proceed to the next iteration. But if either of those are null or not matching in values, we should stop in both of those conditions and return false. That is our rule for checking, and it will be translated to a Boolean in terms of code. But the BFS and DFS solutions are different in their core. For breadth's first solution, we are going to need a queue in order to process every breadth of the subtree. But again, the whole trick of this problem is that we need to traverse the both subtrees at the same time. So no worries on that. Instead of one queue, we need two queues to process this. In each level, after shifting a node from each queue to process, we will take a look at our check rules, the same rule of either of nodes are null or they don't match in values together, which they are in this case. And then as a regular BFS traversal, we will push left and the right child of that node to the end of the queue to be processed through next iteration in the same order that they've been added to the queue. And finally, we are clear with queue and seems like all nodes are equal, so we should return true in that case. But before that, I need to mention something small about the code implementation that I skipped to show in here. What will happen when we are processing the last node and we are at the end of our last steps? Even if the values are going to be equal from both subtrees, we will push null values of this node's left and right child into the queue. And same goes for this tree in here as well. So in order to prevent nodes being null error while processing any node, we need another check to see if a node is null and skip them. I'll show it in the code soon. Okay, enough of detour for now. Let's get back to this state. After processing trees, what is left in the queues will define if both subtrees are equal or not. Because if there are some nodes left in either of those queues, let's consider this situation for example, that would be a signal for us that there are some unprocessed nodes left. Subtrees are not equal and we should return false. So if both of queues were empty at the end, that would be our guarantee that subtrees are equal. But if we are going to process both trees, then how on the face of earth we could end up with unprocessed nodes in either of queues? That I'll show you in the code. So let's jump right into it. For BFS solution, first we need to initiate our queues and manually put the root nodes as first element in the queue. The reason that we always put first node in BFS required queues manually is that there has to be a way to trigger the next while loop we are going to create. So we will check as long as both queues has some values within them. Then we are going to process the queues. That is our key to process the both queues at the same time. So here comes the usual BFS structure. Shift the node from queue and process them. Then it comes the time for our valuable check of if either is null or if values are not matching. Then we might return false immediately. Now we need to add left and right children of both nodes into their relative queues. Remember that if we are at the last breadths, the left and right children would be null for leaf nodes, right? So we could have pushed null values to the queues, the same thing that we discussed in the slides. So if both of them are null, we might continue to finish processing queues. Here comes the time that I promised you to show in the code. Remember that if we are at the any nodes from last breadths of the tree, the left and right children would be null for the leaf nodes, right? So we could have pushed null values to the queues. So before everything that we wrote from line 22 to 30, we need to check if both of the nodes from queues that we shifted out are null, then we need to continue to the next iteration. Finally, as we discussed, if all nodes in the queues were processed and until now that we are out of our while loop and we did not return false based on our checks here, the only thing that would be or guarantee that subtrees are same is the length of queues. If either of them still contains some unprocessed nodes, then we might return false here, right? Because look at the condition that we based our while loop upon. We always check if both queues has lengths of larger than 0. So if either of queues runs out of nodes early, the other one will still contain some unprocessed nodes. And that comes to our help in here to ensure that we have processed them all. So if both ran out of nodes, then it's okay to return true, meaning subtrees are same. Now, if I run this, tests are passing, and if I submit, we are in a good shape here. Now let's go back to the slides to cover the DFS solution. For depth first solution, you already have the whole picture, and in DFS traversal, we will use recursion. So let's think about what could be our base cases. One possible base case is both nodes in the recursion depths are empty. If so, we might return true because that would mean we are at the last depths of a pass, and if we come that far, considering node values until that depths were equal, which they are in this case, then it is okay to have null values there, because we are at the end of that pass. The other edge case would be, again, like BFS solution, if either of the nodes were null or the values of them were not matching, we might return false for this obvious situation. Okay, what is left now? In our recursive procedure, just call in the function itself for both subtrees, passing left nodes once and right nodes to another recursive call at the same time. And if they both return true for each step, that would mean that nodes are same. And we should go to another depth and do the same check. That's simple. Let's implement this solution now. So we are back in Leetcode. For DFS solution, our job is simple here. First, we need to check if we are at the depths, meaning if both P and Q are null. And if so, we might return true because what we are going to cook up next will guarantee that we are safe about this line. Next step is checking if either of nodes are null or their values are not matching, which we will obviously return false for it. And finally, if we call the isSameTree function recursively, pass both left nodes from subtrees, and we call it again, passing both right nodes this time, and the result of that is true, then we are good because we are going to pass both checks that we discussed about. That means values on both left and right subtrees are same. Now, if I run this, test cases are passing, and if I submit, we are in a good shape here. Now let's jump back into the slides to cover time and space complexity. So the time complexity will be O of n for both solutions. N would represent the number of nodes in the tree, since we would visit each node in each subtree once through our iteration. And the space complexity also will be O of n for both. For iterative solution, it's because of queues, and for recursive solution, because of call stack. That was it for this video. Thanks for watching, and please leave a like, comment, and subscribe to the channel. I will put a few more links about different playlists in the description for you to check it out. And finally, hope you enjoyed this video and stay tuned for next one.